So what we're going to go ahead and do today is finish up Chapter 3, and then I'll throw a quiz at you, and then we'll move into the PSS chapter if you're using the 7th edition, or Chapter 2 if you're using the 6th edition, or potentially earlier. The 7th edition, it's known as the PSS. There's a name for it. Actually, when we get to that slide, they give you a name. It's like the Practical Scientific Studies, something weird like that. Pretty much what it does is just go over the basic mathematics. A lot of it's sig figs, significant figures, which is not a particularly fun thing to deal with, but a necessary evil when doing any kind of science or calculations. We did talk about potential and kinetic energy, so I went back through and kind of rearranged those slides a little bit. I came up with some more pictures. We talked about the hydroelectric dam as generating energy. We take the potential energy stored in water flowing from a high source to a lower altitude. That release of energy is the kinetic energy, and if we can control that release of kinetic energy, we can generate energy out of it, or we can generate our useful energy, electrical energy. I mentioned the combustion engine. So here's a kind of animation, or not animation, a picture of what's going on within a combustion engine, what's happening at the different stages. We are quite literally exploding gasoline, but in a very controlled fashion to allow us to translate that motion across. And the other big fun one that we talked about, I said we could convert sugar into our energy storehouse, or ATP. So we've got a couple molecules of ATP, and then what it would then translate into as you released energy, ADP. And if you take a look at the difference between these, you'll see at the outside for ATP, there's 3 technically phosphate groups or phosphorus atoms, and ADP, there's only 2. So the big change is we took the energy in that one circled bond and released that. Okay? Or all life stores energy in that bond, and in the release or breakage of that bond, we can convert that across to something else. So it's kind of fun and interesting. Kinetic energy, we talked about it being a representation of motion. And we apply that back to our phases for matter. We had solids, liquids, and gases. Our gases have the highest kinetic energy. So if we keep everything constant, i.e. we don't compare different elements, we take a single atom in its solid phase versus that same atom in its gas phase, the gas phase for that atom is going to have more kinetic energy than the solid phase, okay, as it has more motion. There's other things we could do to compare. We could look at temperature and how that's going to affect the kinetic energy. So if we start at a solid phase and we add heat energy into it, where does that heat energy go? Okay, if we start with liquid water, the first thing that heat energy does is it goes to heat up the water. So we start with room temperature water, and it increases in temperature, or increases in heat. Okay, eventually what happens? We stop increasing the temperature of the water, and it turns into a gas. Energy is still being put into it. Where did that energy go? Because it didn't go into making the temperature change. It went into the now gaseous particles. It went in to cause that phase to transition. So we're adding heat energy, and it's being translated into kinetic energy for each of those particles. Okay? One of the other things I real quickly jumped on was looking at Einstein's expression relating energy to mass. So the first thing we discussed when we looked at mass was a conservation of mass. We can't create or destroy matter in the course of a reaction. Energy happens to be very related to mass, okay? Or mass happens to be related to energy, which means Einstein was able to come up with this expression, energy equals mass times the speed of light squared. So there's a direct relationship between energy and mass. If we must conserve mass, what does that mean about energy? If mass and energy are equal to each other, and mass must be conserved, what does that mean for our energy? Also has to be conserved. Okay, so in the course of a reaction, we can monitor varying things. We could monitor the mass. We could also monitor the energy. And we would know in the course of that reaction that the energy can change to different states or different types, but it's always going to be present. Okay? So for instance, if we look at our conservation of energy, the textbook lists off 6 main types of energy that we've probably seen. Heat is something fairly common. Light is a form of energy. Okay, is there a way to think about how light could be energy? Any examples?
The sun.
Okay, how is the sun energy? What are you thinking about when you say the sun is energy?
Well, like for example, alligators lay out in the sun bathe and they don't have energy to go hunt for the night unless it's like a solar panel.
So we could look, I think the alligators lie out in it for the heat, so they're trying to get their body temperature up. But there's other things that actually absorb the light energy, that actually do something with that light energy.
Photosynthesis.
Photosynthesis. All plants are absorbing light energy and they convert it into chemical energy in the form of cellulose or sugars. Those sugars we then consume or other animals consume. Birds consume it and then the birds are eaten by the alligators. And the alligators then we can eat if we really felt like it. Okay? So our light energy is light is a source of energy. Where else have we seen light as a source of energy? Yep, heard it. Solar power. Okay? We are trying to take advantage of the energy coming from our sun, that light energy, and trying to convert it into something that we can use. Photosynthesis converts it into chemical energy. Okay? Storage in the bonds between individual atoms. Solar energy, what are we trying to convert it into? Electrical energy. Okay? What do we then do with that electrical energy? We can use it for a variety of purposes. One fun purpose, say in this room, we then take that electrical energy and we turn it right back into light energy, okay, so that we can then see everything within the room. How does that energy come through? Well, we're putting electrical energy into our system or into our light tubes. That electrical energy causes our individual atoms within the lights to then get excited and release that energy back out as the form of light. Okay? So we're seeing lots of different ways that we can transfer energy from one position to another, and these happen to be our common ones. Talked about chemical, electrical, mechanical. I think you guys were the ones where I held the ball over someone's head. Okay? We're looking at kind of a mechanical force there. Hydroelectric dams are typically mechanical as well. You're having the rushing water that's moving, causing another thing to move. That motion is our mechanical energy. Look at the very last one, nuclear energy. How does that work for us? What's happening there? We take a look at one of these smaller portions of an individual atom, which technically we haven't covered. We take a look at the nucleus, and that, by sheer existence, has some energy associated with it. If it shifts and changes its orientation or shape, it can release energy. If we control or find the elements that do that, we can then use that release of energy to do something else for us. Okay? So energy is a huge process. It's always happening around us. It's something we're trying to take advantage of. Okay? So the original textbook slides said something about chemical energy. Is conserved in a reaction. I like to change that a little bit. Okay, it's all energy. Okay, all changes involve some kind of change in energy. It's not just a chemical change. Okay, we could look at physical changes. When we move from a solid to a liquid, okay, how did we move from that solid block of ice to a liquid? We had to add heat. Where did that heat energy go? Initially, it heated up the ice to the point where it could then become a liquid. Once it's become a liquid, we've now increased the kinetic energy of that liquid sample. Okay, so we are constantly changing energy from different types into different categories. Okay? One of the examples they give up here is taking a look at water and pumping it full of electrical energy. In the process of doing that, what we can do is actually cause water to split off into its component elements. And we can get hydrogen gas and oxygen gas. Why is that important? Has anybody heard of a hydrogen fuel cell? Anybody? Okay, a few heads shaking yes. Hydrogen fuel cells. The wave of the future, moving to hydrogen fuel cell cars. Okay, it's a neat idea, except we need hydrogen to cause those to work. How do we get the source of hydrogen? Well, currently, we have to pump electrical energy into water. Where did we get the electrical energy from? Burning all the fossil fuels that we would have had to do in the car anyway. Okay? So we have to look at where all of these energy sources are coming from and try and find ways, particularly when we're trying to find environmentally friendly ways, ways that don't impact our environments. We want as zero impact as possible. Okay? So we want to kind of look at that whole chain as far as our chemistry goes. Okay? Questions about that? Really, no questions at all. Okay, then we'll go ahead and pack things up. We'll go ahead and do the quiz now. So I delayed just enough to get enough people in here to start the quiz. I'm going to pass out a small quarter sheet of paper. Please go ahead and write your name on that sheet. And then I'll advance to the next slide. I'll give you 5 minutes to complete the quiz if you need it. If you need less than that, just flip over the sheet. The back side, I borrowed some scrap paper and they just cut it up. Scrap, right? You can use whatever writing utensil you want. Pen, pencil, crayon. As long as I have some ability to be able to read it and interpret it, you'll be okay. If you're finished, just go ahead and flip it over. I'll come around and steal it from, or take it from you. Let's stop these kind of negative things. Yeah, force it. Okay. If everybody finishes before 5 minutes, we'll go ahead and start early. If not, then we'll just deal with it. So there you go. There's the quiz. And we'll go ahead.